Implementation of Advanced Reusable Rocket Technology by Q2 2024. Introduction. In an ambitious move to revolutionize space access and efficiency, a project has been initiated to implement advanced reusable rocket technology by the second quarter of 2024. This initiative, backed by a significant investment of $15 million, aims to enhance launch efficiency by 60%. The project will be structured around 4 key development phases, ensuring a systematic approach to achieving its ambitious goals. Overview of the project. Objective. The primary objective of this project is to develop reusable rocket technology that can significantly reduce the cost of launching payloads into space. By enhancing launch efficiency, the project aims to make space access more viable for a broader range of customers, including commercial enterprises and government agencies. Investment. The $15 million investment will be allocated across various stages of development, from research and development to operational integration. This funding is crucial for advancing the technology and addressing the challenges associated with rocket reusability. Development phases. The project will unfold in 4 distinct phases, each designed to systematically address different aspects of technology development and operational readiness. Phase 1: Research and Development (R&D). The first phase will focus on fundamental research aimed at refining the rocket's design and materials. This phase will involve aerodynamic optimization, enhancing the rocket shape to minimize drag and maximize thrust. Material science, developing advanced materials that can withstand the extreme conditions of multiple launches and re-entries. Performance metrics, establishing baseline performance metrics to guide further development. This phase is critical as it lays the groundwork for all subsequent activities. The research findings will inform design choices and material selections, ultimately influencing the rocket's performance and reliability. Phase 2: Prototype testing. After the R&D phase, the project will transition to prototype development. This phase will involve construction of a prototype, building a scale model or full-scale prototype of the reusable rocket. Rigorous testing, subjecting the prototype to simulated launch conditions to evaluate key performance metrics such as thrust, fuel efficiency, and recovery systems. Data analysis, collecting and analyzing data from tests to identify areas for improvement and to validate the design. Successful testing in this phase is critical for moving forward to full-scale production. It will provide valuable insights into the rocket's operational capabilities and help refine the design further. Phase 3: Full-scale production. Upon successful completion of prototype testing, the project will enter the full-scale production phase. This phase will focus on manufacturing processes, establishing efficient manufacturing processes to produce rockets at a commercial scale. Quality control, implementing stringent quality control measures to ensure that each rocket meets the required specifications. Supply chain optimization, developing a reliable supply chain for materials and components needed for production. This phase is essential for ensuring that the project can meet market demand and deliver rockets that are both cost-effective and reliable. Phase 4: Operational integration. The final phase of the project involves integrating the reusable rockets into existing launch systems and establishing operational protocols for reusability. Key activities will include landing technology, developing and refining technology for safe landing and recovery of the rocket post-launch. Refurbishment processes, establishing efficient processes for inspecting and refurbishing rockets between launches to minimize turnaround times. Operational protocols, creating protocols for launching, landing, and reusing rockets to ensure safety and efficiency. Successful integration of the rockets into existing operations will be vital for demonstrating the viability of reusable technology in real-world scenarios. Investment and efficiency goals. The $15 million investment is intended to cover expenses across all 4 phases of development. The focus on achieving a 60% improvement in launch efficiency is a critical metric for the project's success. This improvement is expected to reduce costs, lower the overall cost of access to space, making it more feasible for a wider range of customers. Increase launch frequency, enable more frequent launches due to reduced turnaround times and operational costs. Broaden market access, open up opportunities for commercial enterprises, researchers, and government agencies to utilize space for various applications. Key insights and trends. The advancement of reusable rocket technology is seen as pivotal for the future of space exploration and commercial satellite deployment. Key insights from various sources highlight: cost reduction. The ability to reuse rocket components can drastically lower the costs associated with launching payloads into space, addressing a long-standing barrier for many potential users. Sustainability. The project aligns with broader trends in the aerospace industry, where companies are investing in sustainable and cost-effective technologies. Innovations in materials science and engineering are playing a crucial role in these advancements. Collaborative efforts. There is a growing collaborative effort across sectors to drive progress in aerospace technology, emphasizing the importance of partnerships and shared knowledge. Differences between sources. While there is a consensus on the project's goals and development phases, differences may arise regarding specific technologies and methodologies proposed for achieving the outlined efficiency gains. Some sources may provide a deeper dive into technical specifications, while others may focus more on economic implications and potential market impacts. Timeline of events. Q4 2023, project initiation and allocation of the $15 million investment. Q1 2024, completion of the R&D phase and transition to prototype development. Q2 2024, expected completion of prototype testing leading towards full-scale production. Conclusion. The implementation of advanced reusable rocket technology represents a significant step towards revolutionizing space access. With strategic investment and focused development phases, this project has the potential to redefine the landscape of commercial spaceflight, making it more accessible and economically feasible. Successful execution of the outlined phases will not only enhance launch efficiency but also contribute to the broader goals of sustainability and innovation within the aerospace sector. As the project progresses, it will be closely watched by industry stakeholders and could set new standards for future space endeavors. The implementation of advanced reusable rocket technology by Q2 2024 entails a multifaceted approach that is both innovative and ambitious. The project is structured into 4 distinct development phases with a strategic investment of $15 million aimed at enhancing launch efficiency by 60%. The approach taken involves systematic refinement and testing, ultimately integrating these rockets into existing launch systems. Counterintuitive insights. 1. Focus on reusability versus novelty. A common perception in space exploration is that innovation requires entirely new technologies. However, this project emphasizes that enhancing existing reusable technology can lead to revolutionary improvements in efficiency and cost. This implies that the path to advancements in space exploration may lie more in optimizing what is already available rather than inventing new solutions from scratch. 2. Investment versus market viability. The $15 million investment may seem substantial. Yet in the context of aerospace developments, it is relatively modest. This suggests that with focused investments, significant improvements in technology can be achieved without necessitating the massive funding levels typically associated with such high-tech projects. This approach might encourage startups and smaller enterprises to pursue ambitious projects that could disrupt traditional funding models. 3. Efficiency gains beyond economics. While the stated goal is a 60% improvement in launch efficiency, this metric often focuses solely on cost reduction. The counterintuitive aspect here is that enhancing reusability could also lead to environmental benefits by reducing waste and the frequency of manufacturing new rockets. Thus, efficiency improvements may also contribute to sustainability, a factor often overlooked in technical discussions focused on economics. For a phased development approach, the decision to break the project into 4 phases may seem overly cautious or bureaucratic, especially in an industry that often prizes rapid innovation. However, this structured approach allows for meticulous testing and refinement, reducing the risk of failure associated with large-scale implementations. This suggests that in high-stakes projects like aerospace, a methodical approach can lead to more reliable outcomes than a rapid high-pressure development strategy. 5. Integration over isolation. The focus on integrating these rockets into existing systems indicates a shift away from the idea that new technologies must operate in isolation or replace older systems entirely. This counterintuitive perspective suggests that the future of aerospace might depend on hybrid systems that leverage both new and established technologies to enhance overall capabilities. 6. Broader market access. The narrative around reducing costs and increasing launch frequency suggests that space access will become available to a wider range of customers, including smaller commercial entities and government agencies. This democratization of space access is counterintuitive as it contrasts with the typical view of space exploration being the domain of large corporations or government entities, thereby indicating a potential shift in the industry landscape. 7. Technological collaboration. The project highlights a collaborative effort across sectors, particularly in materials science. This raises the counterintuitive idea that advancements in aerospace technology may heavily rely on innovations from unrelated industries, suggesting that the best solutions may come from cross-disciplinary collaboration rather than solely from aerospace-focused research. 8. The role of sustainability. While the primary goal is to improve launch efficiency, the underlying implication is that sustainability is becoming an integral part of aerospace development. This suggests a shift in industry priorities where environmental considerations are increasingly influencing technological advancements, challenging the notion that aerospace innovation is inherently at odds with sustainability. 9. Public perception of space ventures. The focus on reusability and cost efficiency may reshape public perception of space ventures from being viewed merely as high-cost explorations to practical endeavors with tangible benefits, including commercial opportunities and scientific advancements. This could lead to increased public support and investment in space initiatives, challenging the skepticism that often accompanies discussions about space exploration. 10. Timeframe for development. The timeline suggests rapid development within a short period from Q4 2023 to Q2 2024. This may seem overly optimistic given the complexities involved in aerospace projects. However, it reflects an industry trend towards accelerated timelines driven by competitive pressures and technological advancements, indicating that the pace of innovation may be faster than previously anticipated, challenging traditional timelines in aerospace development. Conclusion. The initiative to implement advanced reusable rocket technology represents a significant evolution in aerospace engineering, characterized by strategic investments, structured development phases, and a focus on reusability. The counterintuitive insights derived from this project challenge conventional perceptions of innovation, investment, and market dynamics in the aerospace sector, suggesting a transformative shift towards a more integrated, efficient, and sustainable approach to space exploration. As the project progresses, its outcomes could redefine industry standards and open new opportunities in commercial spaceflight. In the report concerning the implementation of advanced reusable rocket technology, several key aspects may be overlooked by the general audience, yet they hold significant implications for the future of space exploration and commercial launch services. Below are the critical elements that should be emphasized. 1. Granularity of development phases. While the report outlines the 4 development phases, the intricacies within each phase might be understated. For example, the research and development (R&D) phase is not just about refining designs, it involves extensive simulations and modeling to predict how new materials will behave under the unique stresses of repeated spaceflight. The significance of this phase lies in its potential to innovate with materials like carbon composites or alloys that can withstand higher temperatures and stresses, thus extending the lifespan of rocket components. Overlooking this detail might lead stakeholders to underestimate the complexity and duration of the R&D phase, which is foundational for the success of subsequent phases. The R&D phase is crucial for ensuring that the rockets can survive the rigors of multiple launches without significant degradation, which is central to achieving the projected 60% increase in efficiency. 2. Prototype testing as a risk mitigation strategy. The prototype testing phase is not merely a step toward full-scale production but serves as a critical risk mitigation strategy. During this phase, potential failures can be identified and addressed before committing to full-scale production, which involves significant financial expenditure. This phase allows for adjustments in design based on real-world performance data, making it a vital step in ensuring safety and reliability. Ignoring the importance of prototype testing may lead to underestimating the potential risks associated with launching reusable rockets, which, if not adequately tested, could result in catastrophic failures. It is significant because any failure in this phase could set back the timeline substantially and increase costs beyond the initial budget. 3. Economic implications of launch efficiency. The report emphasizes a goal of enhancing launch efficiency by 60%. However, the broader economic implications of this improvement are profound yet might be overlooked. Increased efficiency means lower costs per launch, which could democratize access to space for smaller companies in countries with limited budgets. This shift could spur a new wave of innovation and investment in the space sector, potentially leading to new industries related to satellite technology, space tourism, and beyond. Furthermore, the reduction in launch costs could create a ripple effect across various sectors that depend on satellite technology, such as telecommunications, agriculture, through precision farming and environmental monitoring. Thus, the potential economic benefits of this project extend far beyond the aerospace sector, influencing global markets. 4. Operational integration and its challenges. The operational integration phase is critical as it involves merging the new technology into existing launch infrastructures. This process is often fraught with challenges, such as the need to train personnel on new systems and ensure compatibility with current operational protocols. The significance of this phase is often understated, as many assume that technological advancements can seamlessly fit into existing frameworks. In reality, operational changes often require a cultural shift within organizations, which can be a significant hurdle. Issues such as scheduling maintenance and recovery of reusable rockets may introduce complexities that require careful planning and execution to avoid delays and cost overruns. 5. Collaborative innovations in materials science. The report highlights the role of materials science and engineering in the development of reusable rockets. Yet it does not delve into the collaborative nature of these innovations. The advancements in materials are not solely the result of aerospace companies, they often involve partnerships with universities and research institutions that specialize in materials science. This collaborative approach is significant because it fosters a culture of innovation that can lead to breakthroughs not just in aerospace but in other fields as well. For instance, advancements in lightweight, heat-resistant materials may find applications in automotive or renewable energy sectors. Recognizing the interconnectedness of these innovations can inspire further investments and collaborations that drive technological progress across industries. 6. Potential market disruption. The report mentions that the project aims to make space access more viable for a broader range of customers, including commercial enterprises and government agencies. However, the potential for market disruption is profound and may be underestimated. The rise of reusable rockets could challenge the current market leaders in the aerospace sector, as new entrants with lower operational costs can disrupt existing pricing models. This could lead to increased competition driving innovation and further reducing costs, which benefits consumers and accelerates the pace of space exploration. 7. Sustainability and environmental impact. While the report touches on advancements in sustainable technologies, the environmental impact of reusable rockets is a critical aspect that warrants more attention. The aerospace industry is increasingly scrutinized for its carbon footprint, and the development of reusable rockets could mitigate some of these concerns by reducing the number of rockets needed for launches and minimizing waste. This aspect is significant as public and governmental pressure mounts for industries to adopt more sustainable practices. By highlighting the sustainability of their technology, companies can improve their public image and align with global sustainability goals, which is increasingly important for investors and consumers alike. Conclusion. In summary, while the report provides a comprehensive overview of the implementation of advanced reusable rocket technology, several crucial details deserve further emphasis. The granularity of development phases, the importance of prototype testing, the economic implications of increased launch efficiency, the challenges of operational integration, the collaborative nature of materials innovation, the potential for market disruption, and the sustainability considerations represent critical dimensions of this project. Understanding these nuances can help stakeholders appreciate the full scope of the initiative's impact on the future of space exploration and the aerospace industry at large. 1. Phased development approach. The project is structured into 4 distinct phases: research and development, R&D, prototype testing, full-scale production, and operational integration. This systematic approach allows for incremental improvements and thorough testing at each stage, ensuring that the technology is robust and effective before moving on to the next phase. Analyzing this phased methodology can provide insights into the risk management strategies employed in high-stakes aerospace projects. 2. Significant investment for enhanced efficiency. The $15 million investment is targeted at achieving a 60% improvement in launch efficiency. Understanding the allocation of this budget across the different phases can shed light on the economic considerations driving advancements in reusable rocket technology. This point invites discussion on the financial viability of such investments in the aerospace sector and their potential impact on the cost of space access. 3. Technological innovations and trends. The initiative is aligned with broader trends in the aerospace industry, emphasizing sustainable and cost-effective technologies. This includes advancements in materials science and engineering, which are critical for developing reliable, reusable rockets. Delving into the specific innovations being pursued can highlight how technology is evolving to meet the demands of modern space exploration, sparking a discussion on the future of aerospace engineering practices. For market implications of reusable rockets, the ability to reuse rocket components could revolutionize the commercial spaceflight industry by significantly lowering the costs associated with launching payloads into space. This point can lead to a comprehensive analysis of the potential market impacts, including how increased launch frequency could democratize access to space for a wider range of users, from commercial enterprises to government agencies. Such discussions can encompass the competitive landscape and the strategic positioning of companies involved in this technological shift. 1. SpaceX Falcon 9 Reusability Program 2010-present. SpaceX initiated its Falcon 9 rocket program with an innovative approach to reusability, seeking to dramatically reduce the costs of space launch services. The Falcon 9 first stage is designed to land back on Earth after launch, allowing it to be refurbished and reused for subsequent missions. The program has undergone multiple phases, including the initial development of the rocket, extensive testing of landing systems, and subsequent operational flights. SpaceX's successful reusability strategy has led to a significant decrease in launch costs, making space more accessible to a variety of customers, including commercial, governmental, and international entities. 2. NASA's Space Shuttle Program 1981 to 2011. The Space Shuttle program was a pioneering effort in reusable spacecraft technology, allowing NASA to conduct numerous missions to low Earth orbit. The shuttle consisted of a reusable orbiter, solid rocket boosters, and an external tank. The program aimed to reduce the cost of access to space through the reusability of the orbiter and boosters. Although the external tank was discarded after each flight. Over its 30-year duration, the Space Shuttle flew 135 missions, contributing significantly to space science satellite deployment and the construction of the International Space Station. Despite facing challenges and tragedies, the program established foundational practices for reusable technology in space exploration. 3. Blue Origin's New Shepard 2015 present. Blue Origin's New Shepard rocket is designed for suborbital flight, focusing on space tourism and scientific research. The vehicle features a fully reusable first stage that can land vertically after launch, allowing for multiple flights with minimal refurbishment. The development has proceeded through phases of testing and operational flights, demonstrating the technology's reliability and effectiveness. Blue Origin's vision emphasizes reducing the cost of access to space while promoting sustainable practices in aerospace technology, aligning with broader trends in the industry toward reusability. New Shepard's successful missions have opened new avenues for commercial spaceflight and research opportunities. Future outlook: Advanced Reusabl rocket technology by Q2 2024. 1. Enhanced launch efficiency and cost reduction. The implementation of advanced reusable rocket technology is poised to revolutionize the aerospace industry by significantly enhancing launch efficiency. With a targeted 60% improvement in operational efficiency, the cost per launch will decrease, making space access more affordable for both commercial entities and governmental organizations. This reduced cost structure is likely to spur an increase in the frequency of launches, enabling a broader range of missions, including satellite deployments, lunar exploration, and potential manned missions to Mars. 2. Growth in commercial space sector. As the technology matures, the commercial space sector is expected to see substantial growth. The accessibility of space will attract a diverse array of customers, including startups, established tech firms, and international space agencies. New business models such as on-demand satellite launches and space tourism are likely to emerge, driven by the reduced costs and increased launch cadence. The growing interest in satellite internet services, e.g. Starlink and Earth observation satellites, will further stimulate demand. 3. Technological innovations and collaborations. The project will likely foster a wave of technological innovations, particularly in materials science, propulsion systems, and recovery technologies. The successful completion of the 4 development phases will not only enhance the rocket systems but also lead to potential spin-off technologies applicable in other industries. Collaborations between aerospace companies, academic institutions, and government research agencies are expected to increase, promoting knowledge sharing and accelerating advancements. 4. Sustainability in space operations. Sustainability will become a critical focus as the aerospace industry moves towards more environmentally friendly practices. The ability to reuse rocket components aligns with global efforts to reduce waste and carbon footprints. Future developments may include the use of green propellants and technologies aimed at minimizing the environmental impact of launches. The push for sustainable operations will likely become a key selling point for companies, influencing customer preferences and regulatory frameworks. 5. Global competition and geopolitical implications. The advancements in reusable rocket technology will intensify the global competition in the space sector. Countries that invest in these technologies may boost their geopolitical standing by enhancing their capabilities in space exploration and satellite deployment. This competition could lead to increased collaboration on international projects such as the Artemis program or the International Space Station, as nations recognize the benefits of shared resources and knowledge. 6. Evolving regulatory landscape. As the commercial space industry expands, the regulatory framework governing space operations will need to adapt. Governments will face the challenge of creating policies that ensure safety, sustainability, and equitable access to space. The successful implementation of reusable rocket technology will likely influence the development of new regulations regarding space traffic management, debris mitigation, and environmental standards, ensuring that growth in the sector does not come at the expense of safety or ecological balance. 7. Advancements in launch infrastructure. The integration of reusable rockets will necessitate advancements in launch infrastructure. This includes the development of specialized landing zones, refurbishment facilities, and logistics systems for quick turnaround times between launches. Investment in ground support technologies and facilities will become crucial to accommodate the increased frequency of launches and ensure operational efficiency. 8. Public interest and support for space exploration. The successful deployment of advanced reusable rockets could reignite public interest in space exploration. As missions become more frequent and diverse, public engagement through educational outreach, media coverage, and potential participatory opportunities, e.g., citizen science projects, will likely increase. This heightened interest may lead to greater support for government funding and international collaborations in space science and exploration initiatives. 9. Timeline of expected developments. Q4 2023, project initiation and investment allocation. Q1 2024, completion of R&D phase, refining designs and materials. Q2 2024, prototype testing expected to conclude, followed by the transition to full-scale production. 2025 and beyond, full operational integration and the commencement of commercial launches, with continuous improvements based on testing data and operational feedback. 10. Conclusion, a new era in space access. The implementation of advanced reusable rocket technology by Q2 2024 signifies a pivotal moment for the aerospace industry. The predicted advancements across multiple dimensions, efficiency, cost, sustainability, and collaboration, will reshape the landscape of space exploration and commercial launches. As the project progresses, it is anticipated that the implications will extend far beyond individual missions, influencing global economic dynamics and inspiring future generations to pursue careers in science, technology, engineering, and mathematics (STEM). The successful realization of this initiative could lead to a more interconnected world where space is not just the final frontier but a new frontier for innovation, collaboration, and exploration.